Okay, hello and welcome everybody. Happy to have another Security Week webcast today. This one, again, is a topic that's near and dear to me on industrial cybersecurity. The topic is the missing links for managing OT cyber risk. My name is Mike Lennon. On behalf of Security Week, I'll be the moderator for today's session. A couple quick items before we get started. This is live and designed to be interactive, so feel free to submit your questions through the Q&A box in your On24 interface. We'll most likely save them for the end for the Q&A session, but feel free to submit them throughout while they're top of mind. Additionally, toward the end, we're going to do a couple poll questions, so hopefully you can stick around and participate in that. Additionally, this environment is designed to be customizable, so you can drag and drop the windows, make them bigger or smaller if you need the slides bigger. If you want to see Andrew's face a little bigger on your screen, feel free to adjust those windows and kind of make it to your liking. You also notice some resources in the environment. Those are just links to some reports and additional information. Without further ado, I'm going to go ahead and introduce our speaker today. Many of you in the industrial cybersecurity space may know him already. Waterfall has been in the space for quite some time, as has Andrew. So happy to introduce Andrew Ginter. He is VP of Industrial Security at Waterfall Security Solutions. So Andrew, I'm going to pass it on over to you.
Okay, thank you, Mike, and thank you everyone for joining us. Our topic today is cyber risk. A lot of people imagine that cyber risk is all about cybersecurity. It turns out there's more to it than that, and that's our topic. Give me a moment. How do I advance this? There we go. And so, let's start with incidents. Let's start with consequences. There's a new report out that I'll put the URL on the screen in a minute, talked about cyber incidents with physical industrial consequences. We're talking process industries, we're talking manufacturing industries, we're talking outages, we're talking equipment damage or worse. But we're talking process, and we're not talking hospitals, we're not talking education, we're not talking, government shutdowns. We're talking physical consequences of cyber attacks. What was there? Well, in 2010, there was Stuxnet, destroyed 1,000 centrifuges. In 2011, there was nothing in the public record anyway. And this is all off the public record. 2012, there was a shutdown of an Iranian oil terminal, presumably by hacktivists. 2013, there was nothing. 2014, there was a German steel mill, unidentified, went down, but it was widely publicized. It's in the public record. Massive damages because of a cyber attack. This is what happens when you have to do an emergency shutdown on any kind of smelting operation. The smelter solidifies, the molten metal solidifies, and now you've got a real problem. 2015, the only incident in the public record there was an outage due to cyber was the power outage in the Ukraine late in the year. Almost 250,000 people. The worst of it was an 8-hour outage. 2016, there was another attack, attributed to Russia or Russian actors on Ukrainian power system. This time, just the city of Kiev. In 2017, there were 4 incidents. Triton was the one that targeted safety systems. Triton shut down one facility twice. It shut, a different business, a different enterprise, a different incident. Another facility was shut down. NotPetya had, I said 4, it's 5. NotPetya was attributed again to Russian-sponsored actors. Had a lot of victims, shut down Maersk, the world's largest container shipping company, shut down Merck, a large pharmaceutical company. But it was one incident because it was one piece of, erasure, disk deleter that got inserted into a security update and was distributed automatically to a lot of victims. There was an auto parts manufacturer in North Carolina, and a second one that WannaCry hit. So 5 incidents in 2017. 2018, there was nothing. 2019, there were 4 incidents. We probably all heard of Norsk Hydro. There was an unnamed gas pipeline that was widely publicized. It was down for 30 hours because of ransomware, and some lesser incidents. 2020, there were 9 incidents. In manufacturing, in you name it, there was a brewery that went down. There was a semiconductor fab that went down. Most of these incidents hit multiple sites, down for between a day and up to, I think, 2 weeks on the outside. Last year, there were 22 incidents. We all heard about Colonial. We probably haven't heard of the rest of these, but there's a trend we're starting to see here. We're projecting this year that we're going to see 50 incidents. Here's the thing. What we're observing is arguably a state change in the nature of OT cyber risk. Does anyone believe we're ever going to see a year with 0 incidents ever again? I don't. Most of these incidents are ransomware. Almost all of them are targeted, whether it be hacktivist or ransomware. Targeted meaning the bad guys operate the malware remotely. They are, coming into the network. They get a foothold. They send commands. They get responses. They're manually in there, sort of, one-on-one against the defenders. The shutdowns, sometimes the hacktivists or the ransomware targets the industrial network specifically. Sometimes it targets the IT network, and the industrial network is shut down. The buzzword is in an abundance of caution. It's because, the victim does not trust the strength of their IT-OT interface, does not trust the strength of their OT security program, and so says, the attack from IT might leak into operations. We better shut down. This was Colonial. Sometimes these shutdowns, think a railway system, a passenger rail system that depends, in a sense, completely on the correct operation of the ticketing system. If the ticketing system's on the IT network and goes down, well, the rail system has to be shut down. So sometimes in these industrial incidents were because the industrial network had to be shut down because something it depended on was shut down in the IT network. There's debate sometimes. There are experts out there who say, these really aren't OT incidents. If you target the IT network and IT goes down and you shut down OT out of an abundance of caution, that's not a failure of the OT thing. That's a problem for the IT people. I argue nobody cares. Okay, this might be a hair that engineers on the OT security program or security analysts in the IT security program, they might want to split that hair. Nobody else cares. The business says we suffered a production loss because of a cyber attack. We need this fixed. Here's the bad news. If this wasn't bad enough, the ransomware groups are tracking nation-state attack tools and techniques by about 5 years. It used to be that we would look around and we would say, oh, but we're just a little power plant, we're just a little brewery. Why would a nation-state actor come after us? We know they can do nasty stuff, but why would they come after us? Well, what we're observing is that these ransomware attacks are using what used to be nation-state attack techniques, tools and techniques. The targeted thing was pioneered in 06-07 as advanced persistent threats by alleged Chinese actors. The supply chain thing was pioneered with NotPetya in 2017, and we just saw Kaseya, the first ransomware-based supply chain attack, in 2021. So what we see the nation states doing to each other today, ransomware is going to be doing to all of us within 3 to 5 years. It's going to be doing to all of us with money, and all of us in this space have money. We're all going to be targets. So this is sort of the nature of the world. These are all insights from a threat report that is out on the ICS Strive repository that you might be interested in downloading. So our topic is risk, and in a sense, how risk is different from security, and what are some of the missing links in terms of dealing with risk. Let's look at risk sort of generally first. The the classic formula for risk is that risk is equal to consequence times likelihood. And nobody can calculate exactly what the likelihood of a serious incident is. And so we use qualitative metrics. We say, unlikely is a 1, very likely is a 5. Low consequence is a 1, very high consequence is a 5. But, there's serious problems with this model for risk in the industrial space. One of them is if I have a very likely event, people have stolen the password to, access the file server and pull information about the, what entertainer is going to be at the corporate Christmas party. What are the consequences? They're almost non-existent. How likely is this breach? Well, when the password gets around, everyone's going to go have a look. Very likely, 5 times low consequence 1. It's got a risk score of 5. But look at, all of the lights going out in North America because of a cyber attack. Very high consequence, 5. How likely is that? Very unlikely, given the security is in place. 1. 1 times 5 is 5. Stealing the Christmas party, entertainer's name, and all the lights going out in North America, they're both ranked as a 5. Yet they're very different things. They demand very different responses. But it's, the number there is meaningless. It's worse than that. Cyber attacks are deterministic. They're not random. When one of these targeted attacks, the targeted ransomwares, comes after us, if they find a way in, they steal a password, they log in, they do their thing, they take down production, we respond, we get everything back up. A month goes by. If we have changed absolutely nothing in our security posture, and no one does this, everyone after an incident changes something, but if we change nothing and exactly the same attacker comes after us, it's almost certain that exactly the same attack against exactly the same target will succeed in exactly the same way. Cyber attacks are more deterministic than random. They're not random equipment failures like stuff wearing out and your brake pad's wearing out and your brake's not working anymore. It's not like that. So a better model for cyber risk is the second equation you see here. This is the model that advanced risk calculations use for physical threats, for let's say terrorist attacks. Here's the model. It's a function. It's not multiplying. It's a function of consequence, yes, intent, because there's a threat actor, a deliberate threat actor coming after us. Consequence, intent, opportunity, and capability. And the function is this: if there's intent to take us down, if the threat actor has intent to take us down, and there is an opportunity, and there's always an opportunity. There's always something left open. There's opportunity to take us down, and the threat actor's ability to attack us is greater than the ability needed to take advantage of the opportunity, then we're going down. If they want us and they're able to get us, we're going down. It's deterministic. This is the formula used for terrorism attacks, and we're going to look at each of these metrics. And my point on the bottom here is that there's always some opportunity. And so the question is not, are we secure? Are we not secure? Security is not a binary thing. Security is a spectrum. The question is not, are we secure? The question is, how high do we set the bar? How capable do our enemies have to be before they can take advantage of the first opportunity, whatever opportunity is left to come after us? So let's look at each of the pieces of the puzzle. Consequence. 2 scenarios. Steelcase went down in 2020. They are a furniture manufacturer. They had 14 plants go down for 14 days. On the end of the year, they had to declare this event to the Securities and Exchange Commission, and they declared no material impact. How could they do that? Well, what happened? They had to bring in emergency responders. The insurance covered that. It was expensive flying these experts in, but insurance covered that. They laid off all their people for 2 weeks. Their people weren't happy. They did not get as much money, in unemployment insurance from the government as they got as salary. And they clean up the mess. And they brought their people back and they said, well, we have spare production capacity. We are behind 2 weeks on, delivering our orders. And they scheduled extra shifts. The workers worked long hours. They got overtime pay. At the end of the year, the workers had more money in their pocket than they would have had before the incident because of the overtime pay plus the government unemployment insurance. The company was right up to date on all of its shipments. Okay, they produced everything in the year that they planned to produce, shipped everything in the year that they shipped. The only thing they were out was the overtime pay to the workers, and that was a rounding error on the annual report. This is an example of, it's a physical outage caused by a cyber attack, but it's a physical outage that is acceptable. It's an acceptable business consequence for the cyber attack. Look at Colonial. In contrast, Colonial went down for 6 days, widespread gasoline shortages in the northeastern United States. Colonial provided something like 40% of the gasoline to the northeastern United States. Lots of people, including the regulator, said this is an unacceptable outcome. We expect you to do better than this. And so 30 days after Colonial, the regulator, the TSA, issued new rules for large pipelines and demanded that a security system be put in place that is so robust that if the IT system were ever compromised again, physical operations would continue at full capacity, unimpeded for at least some period of time. So, an example of an unacceptable physical consequence. And it's the consequences that determine the required defenses for a network. Consequences define network criticality. They define, what we need in terms of our security system. But again, it's not typical consequence, it's worst case consequence. When we're looking at the furniture manufacturer, if the 2-week outage really was the worst case, well, it's an acceptable business consequence. You can model the production network as a business network if you want, risk-wise. With Colonial, it was seen by the government, at least, as an unacceptable physical consequence, and they demanded additional security. It is the worst-case consequence. Imagine that every computer in your network, every PLC, every SCADA system, everything is completely compromised, and every one of these computers is doing everything that it can to cause an unacceptable physical outcome. If the very worst case is an acceptable business loss, in a sense, you've got one kind of problem. It's a much simpler problem. And this is much more common, if the very worst case is unacceptable, we need stronger protection. Let's talk about intent. Here's the problem. Intent is usually assumed to be a 1. We assume there's, the bad guys intend to come after us. Why? Because modeling intent accurately is almost impossible. It's very difficult to do. Intent is about motive. The bad guys, all of them in the world, want to come after us. Intent can be useful in, let's call it physical assaults, where you have terrorist groups, where you have deep intel as to what the terrorist group intends to do, because we have people, there's spies in the group, there's communications that's been intercepted. If you have deep intel and you can model intent, you can say if it's a 0 or 1. But most of us mere mortals should assume it's a 1, with one exception, and that is ransomware. The 22 attacks last year, the 22 incidents, there were many more attacks, the 22 incidents were examples of ransomware. And 22 out of the, over 100,000 sites in the world that could be industrial, victims of ransomware. That's a very small fraction. And so when we're talking about ransomware, selecting targets is potentially, modelable as a likelihood, 22 out of 100,000. But here's the thing: even if we model it that way, we're going to have to explain to our bosses if we go down. If we get hit and we go down, and we have to explain this after the fact, what are we going to say? We knew that the ransomware, the standard ransomware attacks were more capable than our defenses. That if they came after us, we were going to go down. We knew that. We just didn't think they'd pick on us. We're going to be fired. Okay, that, you know, using that likelihood as a defense for not doing anything when the pervasive threat environment includes threat actors who could take us down if they just, you know, looked our way and, you know, hit us with what they've got, hit us with their usual, is probably unacceptable. It's probably not due care, which is what the insurers expect of us. And I'm coming to that in a minute. Capability. You know, the bad guys today, I said, you know, ransomware is running, you know, 3 to 5 years behind nation states. So what should we expect ransomware to be doing to us in another few years? We should expect more cloud-based, supply chain-based ransomware like Kaseya coming at us. We should expect it not just in the IT world, but in the OT world as well. Imagine compromising a small or medium-sized industrial provider with 100 customers and connections from their website or their cloud service into 100, you know, industrial sites all over the world. Compromise that service, send the nasty into 100 or 200 sites at once, and they all go down with ransomware. This is what's coming at us. Today's nation states are defeating two-factor authentication. This is the Pulse VPN two-factor breach that's been on and off for over a year now. We should expect ransomware to be using that class of attack against us in the future. Today's ransomware actors, you know, this is the kind of actor we have to expect to come after us. Due care demands that we are ready for it. And so how can we get ready for it? What can we do? A lot of people imagine that cyber risk management is all about cybersecurity. And they're not wrong. You know, there is cybersecurity involved, but there's also engineering. So imagine a coal-fired power plant. You've got a coal pulverizer. You've got a conveyor taking the powdered coal into a furnace. The furnace blows the powder and air, you know, into the burner, and it ignites almost instantly. It heats a boiler. The boiler is 3 stories, 4 stories tall, full of, you know, boiling water and high-pressure steam. Steam is connected to a steam turbine, and so on. If the boiler overpressurizes, there's a risk that it will explode and kill everybody nearby. So that's a consequence we need to avoid. What are we going to do to avoid it? Are we going to increase the length of the password on the PLC that controls the furnace? Or are we going to go to engineering and say, can't you put an overpressure valve on that boiler, a spring-loaded valve, so that if it overpressurizes, it forces the valve open and the steam escapes and it doesn't blow up in our face and kill us? Engineering is going to say we already have overpressure valves on that boiler. That's standard practice. So when we have unacceptable physical consequences, engage with engineering. Engineering as a profession for a century has been about protecting public safety from physical risk. From houses burning down because of electrical faults in products, from, you know, boilers blowing up in our faces, and so on. This is what engineering does. So security, there's 3 resources I wanted to bring to your attention. You know, Security PHA Review is the first of them. This is the book in the middle here, the white one, written by the folks at Connexus, who have been involved in safety systems forever, published by the ISA. And it says, look, you've got to do a PHA analysis, a process hazard analysis anyway, for your safety systems in most jurisdictions. Take that analysis and ask the question, for each of these unacceptable outcomes, what mitigations are in place? Are all of the mitigations hackable? If they all have a CPU in them and can be hacked, then we have a problem. We have a worst-case cyber attack is able to bring about the unacceptable consequence, the safety consequence. So, and then they say, when you see that, go into it and ask the question, can I insert another physical mitigation, a different, an unhackable physical mitigation, like an overpressure valve or a mechanical overspeed, centrifugal governor on the turbine, so the turbine doesn't go too fast and damage. You know, what can I do physically to get rid of these consequences? And most of the time the answer is I can eliminate these consequences physically with very small changes to the physical process, because this is what engineers do. It's what they've done for decades. Second resource is at the top, the bluish one, Consequence-Driven Cyber-Informed Engineering. The book is called Countering Cyber Sabotage. It's from the folks at Idaho National Labs. Most of the book is about risk assessment, but they've got about 4 chapters on what to do about risk. And they spend most of those 4 chapters, again, talking about physical mitigations. Now, it's a little broader. You know, SPR is focused on safety. CCE is saying, well, there's other consequences, equipment damage, or, you know, even just business loss is so big the business goes out of business. There's other kinds of unacceptable consequences that need to be mitigated here. And again, they say, wherever practical, use physical protection so that the consequence becomes physically impossible. And if you can't do that, if you have a system that's just too complicated for that, instead of software, consider unhackable digital mitigations. What's the difference between hackable digital and unhackable digital? Hackable digital has a CPU. Unhackable digital might have a circuit board with transistors and capacitors that will do something digital, but there's no CPU, there's no software, there's no way it can be hacked. The third kind of engineering mitigation that is underused, under-recognized by IT practitioners coming into the space, and there's a lot of IT practitioners coming into the space. This is normal. There's 50 times as many IT security experts in the world as OT security experts. It's normal for engineering teams to, you know, ask for help from IT security experts. But, you know, these folks coming with, you know, increase the length of the password mindset. They're blind to small engineering changes to production networks as well as the physical system. And that's what SecOT is about. This is the book I wrote 2-3 years ago. It's a book that documents what the world's most secure industrial sites do differently. They ask different questions, they get different answers. They don't ask, how do I protect the information? IT protects information. SecOT sites ask, look, all cyber sabotage attacks, and that's what we're trying to prevent, sabotage of physical operations, all cyber sabotage attacks are information. The only way a control system network, a control system can change from normal to sabotaged is for attack information to enter the network somehow. And, you know, there's only 2 ways that information can enter the network. It can come in through offline means, you know, USB keys or laptops that we carry into the site. It can come in through online means, usually through a firewall or through wireless or through the cloud or something. And SecOT cites the methodology, physically protects every one of those, typically less than 24 attack vectors. A comprehensive inventory of incoming information flows is also a comprehensive inventory of incoming attack vectors. Deal with those vectors physically. Take the CD drive out of the machine if it's simply not needed for minute-by-minute operation of the machine. Take it out, and now it's not possible, not physically possible anymore for a CD, you know, for attack information on a CD to pose any threat to the you know, that piece of the control system. So physical mitigations wherever possible. The mitigations for offline attacks, like USBs and laptops being carried in, are pretty straightforward. You know, people recognize them. They say, oh, a little more intense than I'm used to, but yeah, it makes sense. The mitigations that are in place for online flows, like through firewalls, surprise a lot of people. A lot of the latest critical infrastructure cybersecurity standards and regulations demand that when you have a criticality boundary, a connection between a safety critical or between a critical infrastructure, a reliability critical network, and a business critical business network, when you have this criticality difference, these standards demand a unidirectional gateway in between the 2 networks. They forbid a firewall to connect 2 networks like that. For anyone who's not familiar, the unidirectional gateway technology, this is something that is defined in the NIST standards. It is a combination of hardware and software. It's defined to be a combination of hardware and software. Usually it's packaged as a single 1U rack mount appliance, but I've called it out in the red box in the center of the diagram here. Everything inside the box is functionally the gateway, but I called it out to make it clear that there's hardware involved and there's software. The hardware is physically able to send information in only one direction, usually from the industrial network out to the world. How does that happen? Well, inside the hardware, there's a circuit board on the left-hand side with a fiber optic transmitter, a laser. There's a circuit board on the right with a fiber optic receiver, and there's a short piece of fiber in between, usually bright orange, usually exactly this long, connecting the sender to the receiver. And now you can send from the industrial network out to the enterprise network, but it's not physically possible to send anything back. There is no laser on the receiving circuit board. It's not possible for that board to send photons back down the fiber into the industrial network. So we're able to monitor the industrial network here out on the enterprise, use the data from the industrial network to, to do business automation without risk to the industrial network. But I said combination of hardware and software. The hardware is one way. The software, in a sense, is the secret sauce. The software makes copies of servers. If we have, a SQL database or a historian database or an OPC server on the industrial network on the left-hand side, the software on the left side of the gateway logs into that data source, username and password, nothing tricky, logs in and asks for all of the latest data. Gets that snapshot of data, converts it to the strange one-way formats, sends it out through the strange one-way hardware, and out on the enterprise network, again, their software receives that nugget, of state information from the industrial network and populates an identical server. If it's SQL on the inside, it's SQL on the outside. If it's Pi on the inside, it's Pi on the outside. If it's OPC HDA on the inside, it's OPC HDA on the outside. And now we've got a server on the enterprise network that has all of the latest data in it. Enterprise users query that server. They connect to that server. They interact normally with the Pi server or the SQL server and get access to all of the data that's allowed to be shared with the enterprise. All the data that's allowed to be shared is already there. The gateway drops that data into the enterprise. It does not matter if chaos consumes the enterprise network. Nothing gets back into the industrial network to affect physical operations. So this is, again, what we see modern standards and practices demanding at criticality boundaries. And the most common criticality boundary we talk about is the control critical versus the business critical boundary that is the IT/OT interface. So that's engineering. Those are engineering solutions to OT cyber risk problems. What about IT security? What about antivirus? What about security updates? What about, intrusion detection? Well, there's still a role for that. This is something that the IT experts coming in to give us a hand, they're going to know this stuff cold. This is what they're going to recommend. What we need to teach them about from the industrial side is we need to teach them about the engineering approach as well, because it's the two of them working together that give you the strongest protection. What do you apply the IT security stuff to sort of most aggressively in the industrial network? We apply it most aggressively to those assets that are still exposed. So if we have, taken 90% of the safety consequences off the table with physical mitigations, unhackable mitigations, they're done. We don't need to think about how do I do IT security to prevent those safety outcomes. They're gone. If we've got unhackable digital mitigations on the rest of the safety outcomes and some of the equipment protection outcomes, they're off the table. That risk is gone. It's not a cyber risk anymore. No cyber attack can bring about those consequences. If we've got a unidirectional gateway in there and that prevents utterly anybody from the internet or from the IT network getting into the industrial network and messing around with it, that risk is off the table. What's left? Well, there might be errors and omissions. Somebody on the inside might give a command that they shouldn't give and mess something up. There might be, there's still possibly residual risks on the physical side. So for example, if one of our PLCs, the only way to reprogram it is with a USB, and you can't glue the port shut. We occasionally have to reprogram it. Well, that USB is still a risk. And so any piece of the industrial enterprise that is still exposed to any kind of incoming information, it's that piece of it that is needs to be protected most aggressively by the conventional information security practices, longer passwords and patching and so on. A specific example I wanted to give you: if there's any remote access mechanisms left in your design, those remote access mechanisms usually terminate in the jump host. There's a VPN, there's two-factor authentication. Ideally, any equipment that is that exposed to remote compromise needs to be protected by IT security mechanisms most aggressively. Turn on automatic updates on your jump hosts, guys, because the jump host is not necessary to minute-by-minute operations. If the automatic update comes in and blue screens the jump host, that's okay. The lights stay on. Clean water keeps coming out of the system. The jump host is a convenience, so we don't have to drive to the site. And, convenience, it's a convenience that, exposes us to real risk. So that's coming up next, how to deal with that calculation. But if you wind up with a jump host in there, patch it 9 ways to Sunday, antivirus it 9 ways to Sunday, application whitelisting it, you name it, protect it. That's where the ITsec approach is most profitably applied in these these residual risks. Let's say a few words about dealing with risk. Classic risk management theory holds you can do nothing, accept the risk, and you always do that for some risks. For cyber attacks that are just so outlandish, you just can't imagine that anybody could pull this off. You don't have to do anything about. You accept that risk. Accept it cautiously, because your idea of what is totally outlandish might be very different from your enemy's idea of what's totally outlandish. So do it with caution. But as a rule, there's always some kind of residual risk that you accept. We can eliminate risk. And this is what the engineering approach does. Put an overpressure valve in there, and the risk of a cyber attack causing the boiler explosion is now physically impossible. You've eliminated that risk. We can mitigate risk, which is reduce the risk. That's what ITsec tends to do. The engineering approach will, the unidirectional gateway will absolutely block anything coming in. But the ITsec stuff, tends to reduce risk rather than eliminate it entirely. And you do that with whatever risk you have left over. And finally, the fourth thing that classic thing you can do is transfer the risk, usually by purchasing insurance. So let's talk about insurance for a second. Generally, you buy the insurance only for acceptable consequences. If ransomware takes down your IT network and you spend 4 days bringing the experts in and erasing it and restoring from backups, and it costs you $8 million and you get that money back from insurance, that's an acceptable consequence. That's why you buy insurance. If the worst case consequence is you go in there and you blow up the boiler and 12 people die, I'm sorry, you can't restore 12 people from backups. Okay, dead people are dead people. This is unacceptable. And so buying insurance for that is a bad idea. We need to deal with that risk, not transfer it to somebody else. Critical infrastructures, insurance is often, you often need some insurance, yes, but it's the wrong solution for the whole thing. I mean, imagine if the lights go out in the northeastern United States again, like they did in 2003. It wasn't a cyber attack in 2003, don't get me wrong, but I'm saying this time, let's say it was a cyber attack. The CEO of the affected utility gets on the CNN News the day the power comes back, 3 days later. Okay, the power's been up for 3 days. It's a disaster. Disaster areas have been declared in 7 states. The CEO gets on and says, "I'm very sorry. This was our fault. We're going to make it good. It was a cyber attack. But I want everybody who lives in this affected region. I want everyone to understand that throughout this entire horrible thing, this company has not lost 1 red cent because we have insurance." He'd be lynched. That's the wrong answer when there are societal consequences. So critical infrastructures, yeah, they buy insurance, but it's, there's an expectation that critical infrastructures are defended as well, not just insured. Insurance is very valuable for small operators, especially operators who are so small, let's say small water systems. They do not have their own experts on staff. If there's an incident, they have no capability to deal with it. That's where you bring the insurers in and erase everything, restore from backups, suffer a 3-day outage, issue a boil water advisory. But insurance is very valuable for small operators. Something to be careful of, especially for the larger operators, cyber used to be included in general damages policies. Generally nowadays, it is no longer. it's increasingly excluded. If you want cyber coverage, you have to buy it separately. The general damages doesn't cover it anymore. And no matter when we talk to an insurer, there's always an expectation that we're doing something to manage the risk. Due care is the expectation. A question about, a common objection that we get in the world of security, in the world of risk management. What's the ROI for cybersecurity? What's the return on investment? This is arguably the wrong question. You can come back to whoever's asking you, what's the ROI on our safety system? The safety system is just something you do. It's expected that you do this. Society expects it. Your people expect it. It's expected. The same is becoming true of cybersecurity, especially when there are unacceptable physical consequences. What's the ROI? It's the wrong question. We need these risks managed the same way we manage our safety risks. Here's another thing. If you want to avoid hearing this question over and over again, we need to avoid going to the well. Go to the well this year and get, X million dollars to expand our cybersecurity program. Oh, wait, the bad guys just got better. Expand it again. Oh, wait, they're still getting better. Here's the thing. When you put safety mitigations in place, the overpressure valve, they tend to stay there. They tend to work for a long time. This is not true of cybersecurity. And so if we, whatever, cyber risks remain, whatever we cannot engineer out, we need to be aware that, basically cyber solutions age very quickly because the bad guys keep getting better. And so if we want to avoid going to the well and having this question asked of us, what we need to do is solve the problem in a sense more thoroughly. Make small changes to the physical process to engineer out the risk. Make small changes to the communications. Put unidirectional gateways in to engineer out the risk. And this way we can put a system in place that is going to stand the test of time instead of going back to the well and having the ROI question thrown at us every year or two. A word about Waterfall, if you'll indulge me. We are the OT security company. We invented the unidirectional gateway. We've been around for 15 years. We are deployed across the planet. We are trusted by all of the different kinds of critical industrial infrastructures all over the world. No matter where you folks are, we have offices all over the world as well to serve you. Some resources if you're interested. The book that the ISA book is available from the ISA bookstore. The CCE book is available on Amazon. The Secure Operations Technology book is available from Waterfall. It's not a book about Waterfall. It's a book about what the world's most secure sites do differently. And in spite of that, Waterfall as a public service makes the book available free of charge. Go to waterfall-security.com/sec-ot. And you can request a copy of the book. We will do our best to get it shipped to you. Supply chains and shipping are still a challenge sometimes. Something electronic you can tap into, just go to your favorite podcast app and search for Industrial Security Podcast. You'll find the podcast. Waterfall sponsors the podcast as a public service. There's a different expert guest every 2 weeks, every episode, and they talk about their view of the elephant. They give us a deep dive on whatever they are an expert at. And I mentioned the threat report at the beginning. That's brand new. It's less than a month old. It's on icsstrive.com. So finishing up, the expectation, both from society, from our workers, from the insurance companies, the expectation is due care. We have to do the right thing. And what is the right thing changes constantly. But some of the questions that the insurers expect us to ask is, for each of our networks, for each of our systems, what is the worst case consequence? If every CPU is compromised, what's the very worst that can happen? Now, answer the question. That's the very worst. Is that an acceptable outcome? If the toaster factory goes down for 14 days and then it comes back and starts producing toasters again, is that an acceptable outcome? It might be. In which case, we've got the safety issue in, the worker safety issue in the plant solved because there's mechanical interlocks. If we need to shut down any of the equipment in the plant, we're good. Model that as a business network, model it as a business risk, model it using information security, off you go. So let me come back to the center bullet here in a second. If the answer is no, if the results of a worst case compromise are unacceptable, we have to deal with it. Ideally, engineer that risk out of the system with physical safeties, with digital safeties, with unidirectional gateways. But in the middle here, even if we decide that a 4-day outage for an automobile plant that produces 1,000 automobiles a day, we're talking 4,000 automobiles behind production. Even if we decide that's an acceptable business consequence, the insurers are still going to ask us, yeah, but did you do something reasonable? Because if there are cheap, simple things you can do to eliminate risk, why wouldn't you do them? Why would you submit a $50 million claim to the insurance company? Why would they pay that if they say you didn't do your homework? It would cost you almost nothing to put, some extra mechanical interlocks or a unidirectional gateway in, and it would have saved you a $50 million outage, and you didn't bother doing it. So there's an expectation not just that we evaluate the criticality of the networks, but that we evaluate the cost of making the networks much more secure. So this is the world we live in. In practice, the sites with only business consequences, with modest business consequences that the insurance company is not going to get all upset about us at, they tend to use ITsec exclusively. Whereas more consequential operations in critical infrastructures, or when there are safety risks, or when there is a risk of equipment damage, or just when there's a big business risk, they tend to use a combination of engineering and SecOT and ITsec protections together. This is what I had for you. We have some poll questions, so if you'd like to think about, giving us some answers here, we'd love to understand, was the webinar useful for you? Was it, how did you hear about it, and so on. I'm going to cycle through these one every couple of minutes. In the meantime, Mike, are there questions and answers that we can go through?
Yeah, we do have a couple questions. Let's see here.
And feel free to answer any of your questions in the Q&A tab. I'd be happy to try and answer them at least.
Okay. Yeah. Well, we have a first question. Okay. A number of comments here. And this is probably a tough one to answer in full, but what sort of situations do you come in? The question is, a manufacturing system may house sensitive intellectual property, I guess, which may not be on the office network, but somehow in the OT network. How do we protect it from cyber theft?
Absolutely, and this is absolutely true on. You tend to see it more in discrete manufacturing. You're manufacturing, aircraft parts or automobiles, or this is where you see a lot more of the proprietary information. And there's in a sense two answers. One is the scenarios I've been focused on is preventing unacceptable physical consequences. If we're talking about preventing unacceptable business consequences, this is something that the IT people are experts at. We need to engage with the IT people and ask, how can we protect this information? Now, one of the engineering tools that, again, the IT people tend to be blind to and the engineers need to remind them of, is the unidirectional gateway. If the gateway is allowing industrial data to get out to the enterprise and nothing gets back, okay, I get that. That makes sense. What it also means is that the gateway is preventing remote control. So if a piece of malware gets into the industrial network somehow on a USB, on whatever, on a laptop, and tries to phone home and say, hey, boss, I got a live one. What do you want me to steal here? As a rule, the attackers don't have perfect intelligence, perfect information about the target network. If something gets loose in the network, it generally is not smart enough to find the information that it's looking for, disguise it as normal process data so that it will be sent out to the enterprise network. You don't have that ability in most of the malware. the way that you steal that information is the malware gets a foothold and someone starts sending it commands to say, okay, look around the network. Oh, there's a file server over there. Okay, go see what's on the file server, and interactively steal the information. That's not possible through a unidirectional gateway. So there are some, there are some ways that the gateway makes certain kinds of information theft much more difficult. But in a sense, it's really a question for the IT teams. They're the experts. They might bring in encryption. They might bring in, data loss prevention stuff. They've got, they've got tools to deal with this problem.
Okay, thank you. Okay, next question. Dan asks, if you have a very large, complex, old OT network with too much connectivity and not enough security, how do you move it toward being more secure? I.e., how do you deal with the size and inertia issue? Good question.
My best answer there is, let's say two things. We've got to make some changes. We've got to recalculate the ROI, and we've got to probably bring some money in. So let's talk about both ROI and money. ROI first. When we put a new system in, we add some functionality to our control system because we want to optimize production. We say, look, it's going to cost us $50,000 to bring the control system in, the new component. It's going to save us $1 million a year. There's ROI for you. Let's do this. And we make the change. Every plant says we're starved for cash, but every time you've got a $50,000 investment yields $1 million return, bang, we make the investment. We make the change. We spend the money. We make the effort. But as part of every one of those projects, we ask, what's the ROI? And we ask, what's it going to do to our safety posture? Oh, look, it blows our safety posture wide open. We're going to see casualties at the site. This is unacceptable. And you go back to the drawing board, and you do not proceed with that project until you've dealt with the safety. Well, this is what we need to do with cybersecurity. If we bring in a $50,000 enhancement that's going to give us $1 million and it blows our security posture out of the water, that's unacceptable. Back to the drawing board. Fix this just like we fix safety, because we're not willing to live with these consequences in these very consequential networks. But if you have made a lot of questionable, or in hindsight, in the day, it was probably making a lot of sense. I mean, a lot of stuff went in before cybersecurity was a thing. But in hindsight, if you say, oh, shoot, the ROI just doesn't look that good anymore. Now we've got a mess. How are we going to fix it? We've got to get some money. Oh, sorry, I'll advance this to the next question before I forget.
Okay, great.
We've got to go to the business decision makers, and we have to, if we go to them and say, cybersecurity, protect the information, they're going to look at us. They're going to say, where's the ROI? If we go there and explain the consequences and say, this is the worst case consequences, if we get hit with one of these ransomware attacks, we're going to go down. If we get hit with something more sophisticated, we're going to go down hard. There's going to be casualties. There's going to be an environmental disaster, whatever it is. Talk consequences to these people. Talk attack scenarios that we're not confident of defeating reliably. And, they add these up to risk. And they say, what's that going to cost to fix that risk? Because, when the business decides to act, the money comes free and we spend it. Nothing comes for free. You can't wave a magic wand and say, there, now suddenly the risk has gone away. We may have to make some changes to our practices. We may have to do things that are a little less convenient and are going to cost us a few extra hours a day or a week. That's sort of the ROI, and we might have to spring some money free. I'm meandering. I hope that made sense.
It did. And okay, another question. I know this one comes up a lot when you have this discussion. So this one is, my concern is how unidirectional control, which could be a data. He mentions a data diode, or in your case, unidirectional gateway. How is it as compared to protect? Sorry, I was trying to reword this on the fly. Basically, how does it compare to next generation firewall methods?
Yeah. So, I did a presentation 3-4 months ago. It's archived on the Waterfall website under webinars, 13 ways to break a firewall. What you don't know will hurt you. It's, in a sense, a refresh on a presentation that I did back in 2012. Here's the depressing thing. I refreshed almost every attack. It's almost all new attacks. And all of the old attacks still work. There's a ridiculous number of ways through firewalls. I can give you a few examples, but nothing gets through a gateway. It's not physically possible. But with a firewall, start with the very simple. Firewalls are software. They might look like hardware on the outside. Open the lid. There's a CPU inside. There's software. All software has bugs. Some bugs are security vulnerabilities. For evidence of this, go look on your favorite software vendors, your favorite firewall vendors' website and see how many security updates they've issued recently. Delay applying one of those security updates just a little bit, and the bad guys are in there exploiting the known vulnerability. Or the bad guys, occasionally discover their own unknown vulnerabilities, 0 days, and come after us. Worse than that, firewalls fundamentally are routers. Now, don't be insulted. Deep inside every firewall is a router because it's forwarding traffic, network traffic, from one network to another. It's a router with a whole bunch of other stuff. The other stuff is looking at every message and asking the question, is this message allowed? And, next-gen firewalls have lots of more sophisticated ways of looking into the message and understanding exactly what the message is and asking the question, is it allowed? If we can persuade that part of the firewall that an attack is allowed, it will happily forward the attack right through the firewall into the industrial system that we're allegedly protecting with the firewall. People imagine that firewalls expose industrial data for the enterprise, so the enterprise can profit from access to the industrial data. People imagine that firewalls give us access to industrial data without giving us access to the industrial system. It's not true. Every message that goes, the only way to get data out of these industrial systems is to send queries in and get answers back. And every query is a potential attack. So lots of different ways that you can break firewalls. None of them work on a unidirectional gateway. For example, the gateway software from time to time has vulnerabilities. The underlying operating system has vulnerabilities. But even if you exploit those vulnerabilities, even a worst case exploit takes complete control of the CPU, the one-way hardware saves you. Nothing gets back. So, for every example of how you can breach a firewall, I go through in those old presentations, a way that it just doesn't work on unidirectional gateways. This is why, increasingly critical infrastructure and other standards demand unidirectional gateways at criticality boundaries. Not every firewall in the industrial network is replaced with a gateway. Not every firewall on the IT network is replaced with a gateway. The gateway goes as extra protection at the boundary between these two networks at different levels of criticality.
Mm-hmm. Yeah, and it's not to say that they don't have their place and aren't extremely effective in protecting networks, because I think we did
Absolutely.
one of
the I recommend firewalls inside the industrial network for horizontal protection inside that network. I recommend them on the IT network. Absolutely. The boundary is what needs something stronger.
Absolutely. Okay, and this one I might need some clarity on this, on terminology. This question is: how do you see semi or fully autonomous OT machines changing the OT security risk landscape and necessary precautions? So I don't know whether they mean like fully autonomous, meaning updating themselves, or just autonomous machines. But if you want to take a stab at that.
Yeah, so this is, in a sense, new ground. Where to begin? I mean, the word autonomous reminds me of a conversation I had with, a mining user group recently. And, they're talking about, we're talking strip mines, we're talking even underground mines, where a lot of the equipment in the mine is got no people in it anymore. The big trucks that run around a strip mine are completely autonomous. Yeah, that's an important and interesting problem. We haven't yet standardized on a solution for that, but it's certainly a question that's worth asking. Beyond that, I mean, every closed loop PLC is to an extent an autonomous thing. And what I'll say in that sort of traditional autonomous operation space is that, any kind of closed loop where monitoring data is used to make a decision, is used to change a set point, is used to change the physical operation, is used to produce more monitoring data, and loop like that, in milliseconds or in seconds, faster than human control can provide. That whole loop tends to live behind a unidirectional gateway. The gateway at the IT/OT interface, you don't have, how many computers on the internet are allowed to control our 3 gigawatt power plant? None, thank you. So there is no closed loop control there. The closed loop tends to happen inside the protected network as opposed to across the boundary. So there's a couple of different answers, but in general, everything is becoming more and more automatic. And, we deploy more and more automation. We deploy more and more computers. We connect those computers more and more. We're deploying more targets steadily. We're deploying more opportunities for attacks, because every connection lets information flow, lets attacks flow. We're deploying more target and more opportunities constantly. The cybersecurity problem is going to get much worse than before it gets any better. This is none of these trends are going to reverse anytime soon. This is why we need to be taking measures right now, engage with engineering, take the most powerful measures we have and use them routinely to put OT risk management programs in place that are going to stand the test of time.
Absolutely. And even, those type of machines, you mentioning kind of an autonomous truck or vehicle driving around, I assume it doesn't necessarily need to be connected to a network that entire time. It can be kind of running on its own. It's got its own sensors. It's got its own kind of, program running where it knows what to do and not necessarily always on a network. So that kind of.
Yeah. So, if we're talking about autonomous automobiles, consumer devices, I'm not an expert in that field. I have all sorts of concerns in that field, but I don't have a lot of solutions. Here's a concern. When we're talking safety systems, I submit that no safety critical system should be connected directly or indirectly to the internet. When I say, what does that mean? If we've got the safety system with no wires and no wireless coming into or out of it, well, that's an air gap safety system. That's good. If you've got it connected to another network, to another firewall, out 17 layers to the internet, that's an indirect connection to the internet. It's going to be breached sooner or later. And here's the thing, automobiles running around, even autonomous automobiles, we don't call them hackers. We call them enthusiasts. Okay, people who open up the vehicle and customize the vehicle. If the safety system in my autonomous vehicle, the one that I depend on for my life, is getting information from nearby automobiles that have been customized, that have been, by enthusiasts, how do I know that that information is trustworthy? Because I'm trusting my life to it. In my estimation, these autonomous automobiles, the safety critical decision making needs to rely on sensors and decisions and systems inside the automobile that are, in a sense, invulnerable to any information coming in from the outside. If you want to use information coming in from the outside, it can be used to optimize the function of your automobile, but it had better not be used for the safety critical functions, avoiding collisions, avoiding, running over pedestrians. So, to me, that's a design principle. But again, I'm not expert enough on what's going on in the automobiles to speak to that.
Absolutely. Okay, we did have a few more questions, but we're pushing about 5 minutes over at this point. So, Andrew, thank you very much for your insights and information. I hope everyone found this useful. Anyone that did register, you'll get a link to watch it on demand. And you'll also get linked to some resources as well from Waterfall. But Andrew, I'll leave it to you for some final parting words. But on behalf of Security Week, thank you very much. And we hope to see you again, and hopefully in person. I think you guys are going to be down in Atlanta for our conference. I hope you'll be down there.
We do plan to be at your conference. I don't know if I'll be there personally, but I want to thank you for this opportunity to bring this topic to people's attention. I want to thank everyone who's stayed with us. And, I hope it was useful. Give us some feedback. We can only get better if we get feedback, good, bad, or ugly. Let us know if this worked for you. Thanks so much.
Thanks, Ginter.